Welcome to Lesson 2 of my Red Pill course on calculus, where we will gain a new view of the universe. In Lesson 1, we based calculus on the following axioms, divided into two groups. In the first group, we have the axioms that deal with the real numbers, the field axioms, the order axioms, the completeness axiom, and the axiom of the existence of R. In the second group, we have the axioms that deal with sets and ordered pairs in general, the axioms of extensionality, separation, pairing, union, power set, ordered pairs and Cartesian products. We imagine the universe of calculus as an infinite totality of things that satisfies these axioms. Now recall that mysterious guy from Lesson 1 who told you that the universe you're exploring is actually very different than you think. As you may remember, he offered you a blue pill and a red pill and said, "Take the blue pill and you'll wake up tomorrow and you won't remember me. You will continue to explore your monochromatic blue universe without knowing the truth. But if you take the red pill, you will see the universe with different eyes. You will realize that it contains blue things and an abundance of non-blue things." Now that you have decided to look at Lesson 2, I know you have chosen the red pill. So let's see what it does. On the basis of the previous axioms, we have already been able to discover many things in the universe. For example, the natural numbers 1, 2, 3 and so on, and also some concrete sets, such as n, z, q, r, or the power set of r. It would never have occurred to us to call these things blue, because the term blue makes no sense at all in the context of mathematics. That's what we thought. But now we learn that although the things that we can define on the basis of the previous axioms are blue, there are many things in the universe that are not blue. Do you see the non-blue things? Good heavens, yes, you might say. I see them, but I can't name them. Don't worry, you'll get used to it. Let's take the example of natural numbers. We know that for every naive counting number, we find a natural number in our universe of calculus, potentially infinitely many. Each of these numbers can be defined as a sum of ones. So all these numbers are blue. However, we cannot conclude that we can reach every natural number, that is, every member of n in this way. Recall that the naive counting numbers, and therefore also the corresponding members of n, are only potentially infinite, while n is an infinite set, and thus an actual or completed infinity. In fact, as an effect of the red pill, we realize that there are also non-blue members in n. So n now looks like this, with all definable numbers lying in the initial range of the blue numbers. The non-blue numbers are therefore greater than all conventionally definable numbers. You may be wondering how this can be, since we have defined n as the smallest inductive subset of R, namely the intersection of the family of all inductive subsets of R, where A is inductive means that 1 is in A, and for all x, if x is in A, then x plus 1 is in A. Hence, n is a subset of each inductive subset of R. This remains true, just as everything we have found out on the basis of the previous axioms remains true. But what about the set of all blue members of n, you might object? Wouldn't that be a proper subset of n and still inductive? Well, no. The reason for this is that the set of all blue members of n does not exist in our universe. All axioms of conventional calculus remain unchanged. Hence, the axiom of separation is only applicable with properties that can be formulated in the language of conventional calculus. But conventional calculus does not know the term blue. Hence, a set of all blue natural numbers does not exist in our universe. Here I must refer you to the package insert of the red pill. It says, you will be able to perceive a new quality of the universe, namely the distinction between blue and non-blue things, but you will not be able to use this new quality to form sets by separation. It is important to understand that this is not a restriction compared to conventional calculus. It is only a condition linked to the enhanced perception we have gained through the red pill. All set formations that were previously possible are still possible, and all statements that were previously valid are still valid. This is why blue pill students and red pill students can talk about the same universe even though they perceive it differently. Imagine Bill from the blue pill course and Ralph from the red pill course meeting during the coffee break. Bill might say, N is the smallest inductive set, isn't it? And Ralph replies, sure, but there are still blue and non-blue numbers in N. We just can't separate them by set theory. Bill doesn't understand. What the hell are you talking about? He thinks Ralph is hallucinating. Ralph, on the other hand, thinks Bill is blind to subtleties such as the distinction between blue and non-blue numbers. Nevertheless, both agree on all the theorems of conventional calculus. So what is the advantage of being in the red pill course? Let's look again at the natural numbers. The blue numbers include all numbers that can be defined in conventional calculus. But beyond all blue numbers, there are non-blue numbers which are greater than any real number that we can define in conventional calculus. In a certain sense, they are infinite, or as we prefer to say, unlimited. We call the reciprocals of these numbers infinitesimal. So, despite the fact that R has the Archimedean property, which remains true, there are unlimited numbers and non-zero infinitesimals in R. Crazy, right? But perfectly logical. As we said at the end of lesson 1, mathematically speaking, the red pill consists of a new primitive notion and 3 new axioms that allow us to see more. How we call the new primitive notion is basically irrelevant. The only important thing is that it has no meaning in conventional calculus and therefore cannot be defined in the language of conventional calculus, that is, using the previous primitive or defined notions. We could therefore continue to call it blue. But in order to be compatible with the mathematical literature, we are now going to call it standard. The new axioms will ensure that our universe of calculus contains things that are standard and things that are not. We will make this more precise in a moment. First of all, we would like to express that non-standard things are inconspicuous in relation to conventional calculus. They are in no way different from the standard things as long as we only consider statements that can be formulated in the language of conventional calculus, that is, without the new predicate standard. This is expressed by the transfer axiom. In the following, we refer to statements formulated in the language of conventional calculus as internal. Correspondingly, we call a statement that involves the new predicate standard, directly or indirectly, that is, through defined terms, as external. We can now formulate the transfer axiom as follows. If phi of x holds for all standard x, then phi of x holds for all x. Here, phi of x is any internal statement with a free variable x. Phi of x may also have standard parameters. that is, defined constants that are standard or other free variables that are restricted to standard values. Before applying the transfer axiom, you have to make sure that the statement to be transferred is internal and that all parameters have standard values. Otherwise, the application of the transfer axiom is illegal and generally leads to false conclusions, just like the division by zero. Attention is therefore required. There is a dual variant of the transfer axiom that looks like this. If phi of x holds for some x, then phi of x holds for some standard x, where phi of x is again any internal statement, possibly with standard parameters. This means that there is no conventionally formulated statement that applies exclusively to non-standard things. How can we derive the dual variant from the original? First, we apply the transfer axiom to the negation of phi of x. This gives, if not phi of x holds for all standard x, then not phi of x holds for all x. According to the rules of logic, we can reverse the direction of any if-then clause if we negate the subclauses. That is, if alpha then beta is equivalent to if not beta then not alpha. In our case, this yields if not phi of x does not hold for all x, then not phi of x does not hold for all standard x. The first subclause means that phi of x holds for some x. The second subclause means that phi of x holds for some standard x. And that's the dual variant. If phi of x holds for some x, then phi of x holds for some standard x. The dual variant of the transfer axiom implies in particular, if phi of x holds for exactly one x, then this x must be standard. This is very important because it means that everything we can define in the conventional language of calculus, that is, with internal statements, is standard. This is the reason why everything we have defined so far is standard. For example, the empty set, the sets n, z, q, r, and also every concretely defined number, such as -1, 2/3, or 10 to the power of 100. Since all these conventionally defined constants are standard, we will no longer mention them explicitly as standard parameters when they appear in a formula. In Lesson 1, we defined some operations for numbers and sets, operations like addition, multiplication, union, intersection, and so on. The definitions were internal statements that uniquely determine the output of the operation for given input parameters. Due to the transfer axiom and its dual variant, the output of these operations must therefore be standard if the input parameters are standard. Here are a few examples. Sums and products of standard numbers are standard. If A is a non-empty standard subset of R that is bounded above, then the supremum of A is standard. Unions, intersections, differences, Cartesian products, and power sets of standard sets are standard. For any given standard x1 to xn, the set of these members is standard. Here n can be 1, 2, 3, and so on. An n-tuple is standard if and only if each of its entries is standard. Here n can be 2, 3, 4, and so on. A standard function returns standard function values for standard arguments. The domain and the range of a standard function are standard sets. Another important implication of the transfer axiom is the following theorem. A standard set is uniquely determined by its standard members, even if it also contains non-standard members. Why is that? Assume that two standard sets A and B have the same standard members. That is, for all standard x, x is in A if and only if x is in B. The formula in the red box is internal with standard parameters A and B. The transfer axiom is therefore applicable, and by transfer we obtain for all x, x is in A if and only if x is in B. Hence, by extensionality, A and B are the same. With the predicate standard, we can now define what limited, unlimited, and infinitesimal numbers are. A real number x is called limited if there is some standard y such that the absolute value of x is less than or equal to y. It is unlimited if for all standard y the absolute value of x is greater than y. It is infinitesimal if for all positive standard y the absolute value of x is less than y. Two real numbers x and y are said to be infinitely close if their difference is infinitesimal. Note that all these defined predicates are external, as their definitions involve the predicate standard. We have now defined what unlimited numbers are. What we are still missing is an axiom that tells us that unlimited numbers exist. We therefore postulate there are unlimited numbers in R. Since R is a field, there are also non-zero infinitesimals in R, namely the reciprocals of the unlimited numbers. And since R has the Archimedean property, that is, n is not bounded above in R, there are also unlimited numbers in N. If we combine different scalings, the real number line looks like this. Around 0, we have the infinitesimals. These are non-standard, therefore shown here in red. On the purple sections, we have the limited numbers, which include standard and non-standard numbers. On the positive side, these also include the standard natural numbers, shown here in blue. In the outer red sections are the unlimited numbers. On the positive side, also the unlimited natural numbers. The following plausible rules apply when calculating with limited, unlimited, and infinitesimal numbers. Sums and products of limited numbers are limited. Sums and products of infinitesimals are infinitesimal. The product of a limited and an infinitesimal number is infinitesimal. The reciprocal of an unlimited number is a non-zero infinitesimal. The reciprocal of a non-zero infinitesimal is unlimited. The defined binary predicate in infinitely close to is reflexive. Each number is infinitely close to itself. Symmetric. If x is infinitely close to y, then y is infinitely close to x. And transitive. If x is infinitely close to y and y is infinitely close to z, then x is infinitely close to z. The proofs are straightforward. As an example, we show rule number 3. The product of a limited and an infinitesimal number is infinitesimal. Let x be limited and y infinitesimal. We have to show that x times y is infinitesimal, that is, that the absolute value of x times y is less than any given positive standard real S. So let S be any positive real number. Since x is limited, its absolute value is less than some positive standard real, say S1. And furthermore, since y is infinitesimal, its absolute value is less than S over S1, which is also a positive standard real. Now we can conclude the absolute value of x times y is equal to the absolute value of x times the absolute value of y, and this is less than S1 times S over S1, which is equal to S. That's it. By definition, every standard real is limited. But are there standard infinitesimals? Well, yes, but only one. We claim that if S is a standard real and infinitesimal, then S must be 0. So 0 is the only standard infinitesimal. That seems plausible, but we can prove it with the transfer axiom. Let S be a standard infinitesimal. By the definition of infinitesimal, we have for all standard x, if x is in R and positive, then the absolute value of S is less than x. The formula in the red box is internal with standard parameter S. We can therefore apply the transfer axiom. Then, by transfer, we conclude for all x, if x is in R and positive, then the absolute value of S is less than x. So the absolute value of S is less than any positive real. Hence, S must be 0. Since 0 is the only standard infinitesimal, two standard reals that are infinitely close are equal. The axiom of separation is only applicable with internal predicates. Hence, the set of all x in A that satisfy phi of x for a given set A cannot be formed if phi of x is external. Such a set term would be just as undefined as the fraction 1 over 0. You can write it down, but it has no meaning because it cannot be defined on the basis of the axioms. We say that external predicates are not set-forming. Now assume that A is a set. We look at the standard members of A that satisfy phi of x, where phi of x is possibly external. In general, they do not form a set, because the conjunction standard and phi of x is definitely external. On the other hand, a standard set is already uniquely determined by its standard members. It is therefore obvious to ask whether the standard members of A which satisfy phi of x can be completed to a standard set, even if phi of x is external. The answer is given by the axiom of standardization, provided A is standard. Recall the axiom of separation from lesson 1. For every set A, there is a set B whose members are exactly those x in A that satisfy phi of x. Here phi of x is any statement of conventional calculus that is internal, possibly with parameters. B is uniquely determined and denoted with this notation known from lesson 1. And B is of course a subset of A. The axiom of standardization postulates the following. For every standard set A, there is a standard set B whose standard members are exactly those standard x in A that satisfy phi of x. Here phi of x may be external, possibly with parameters, not necessarily standard. B is uniquely determined, since a standard set is uniquely determined by its standard members. The designation of the set is similar to separation, only preceded by a raised S. This set is also a subset of A. Why? By the axiom of standardization, we know that for all standard x, x in B implies x in A. The formula in the red box is internal, with standard parameters A and B. Therefore, the transfer axiom is applicable, and by transfer, for all x, x in B implies x in A. Hence, B is a subset of A. Thus, we can read this notation as the standard subset of A obtained by standardization with the predicate phi. The axioms of separation and standardization look very similar. Note that the only difference between the two axioms is that where the axiom of separation speaks of sets and members, the axiom of standardization speaks of standard sets and standard members. What is the effect of this difference? Let's assume that we have a set A of things in our universe, symbolized here by circles, rectangles, and triangles. Our fellow students from the blue pill course see the set A like this, but since we took the red pill, we know that it actually looks like this. There are standard members, shown here in blue, and non-standard members, shown here in red. Let's further assume that we have an internal predicate phi of x that characterizes circles. Since phi of x is internal, the axiom of separation allows us to form the set B of all x in A that satisfy phi of x, that is, the set of all circles in A. In general, separation allows us to form subsets of any set using any internal predicate. The notation for a set defined by separation is explicit in relation to standard and non-standard objects. Now assume that A is standard, and that we have an arbitrary, possibly external, predicate psi of x that characterizes triangles. Since psi of x may be external, we may not be able to use the axiom of separation with psi of x. But according to the axiom of standardization, there is a standard set C whose standard members are precisely the standard members of A that satisfy psi of x. Thus we know that the blue figures in C are precisely the blue triangles in A. But there could, for example, be red non-triangles in C or red triangles outside C. In general, standardization allows us to form standard subsets of any standard set using any, possibly external, predicate. Although this set defined by standardization is uniquely determined, the notation for the set is explicit only in relation to standard objects. It does not tell us anything explicit about non-standard objects. Loosely speaking, you could say that standardization is a kind of separation if you only look at the standard members. Let's take a look at a few simple examples. The standard subset of R obtained by standardization with the predicate limited is the entire set R, because R is, of course, a standard subset of R, and the limited standard reals are exactly all standard reals. The standard subset of R obtained by standardization with the predicate unlimited is empty, because the empty set is a standard subset of R and no standard real is unlimited. The standard subset of R obtained by standardization with the predicate infinitesimal is the singleton with member 0, because this set is a standard subset of R and the only standard infinitesimal is 0. The standard subset of R obtained by standardization with the predicate non-infinitesimal is the set R without 0, because this set is a standard subset of R and all standard reals except 0 are non-infinitesimals. For a standard set A and an internal predicate phi of x, separation and standardization lead to the same result provided that phi of x has only standard parameters. This follows from the transfer axiom. To see this, we define B as the standard subset of A obtained by standardization with phi of x. Thus, B is standard, and for all standard x, x is in B if and only if x is in A and phi of x. The formula in the red box is internal with standard parameters A and B, and possibly further standard parameters in phi of x. Therefore, transfer is applicable, and we conclude that for all x, x is in B if and only if x is in A and phi of x. Hence, B is the set of all x in A that satisfy phi of x. Separation and standardization lead to the same result. However, as soon as phi of x has non-standard parameters, the two sets obtained by separation or standardization may differ. For example, let x0 be some fixed real number. Then x is less than or equal to x0 is a unary internal predicate with parameter x0. By separation, we can form the set of all reals that are less than or equal to x0. This set is always non-empty and a proper subset of R. By standardization, we form the standard subset of R whose standard members are the standard reals that are less than or equal to x0. This is empty if x0 is negative unlimited, because no standard real is less than or equal to a negative unlimited real. It is the entire set R if x0 is positive unlimited, because every standard real is less than or equal to a positive unlimited x0. In these cases, separation and standardization result in different sets. But even in the case where x0 is limited, the two sets can differ. And this is the most interesting case, because it is important for the definition of the standard part of limited reals. By standardization, we can prove the following theorem. Every limited real x0 is infinitely close to exactly one standard real, denoted by STP of x0. We call it the standard part of x0. You can imagine a magnifying glass with sufficient unlimited magnification. If you look at a limited number x0 through this magnifying glass, you will also see a standard number that is infinitely close to x0, the standard part of x0. To prove this theorem, let x0 be limited. Hence, there is a standard u such that negative u is less than or equal to x0 and x0 is less than or equal to u. Define B as the standard subset of R obtained by standardization with the predicate less than or equal to x0. Then for all standard x, x in B implies x is less than or equal to u. The formula in the red box is internal with standard parameters b and u. Therefore, transfer is applicable. And by transfer, for all x, x in B implies x is less than or equal to u. Hence, B is bounded above. Since negative u is standard and less than or equal to x0, we have negative u is in B. Hence, B is non-empty. Due to the completeness axiom, B has a least upper bound S. Since B is standard, S is also standard. We claim x0 is infinitely close to S. That is, For all positive standard epsilon, the absolute value of x0 minus s is less than epsilon. We prove this by contradiction. Suppose the absolute value of x0 minus s is greater than or equal to epsilon for some positive standard epsilon. We have to distinguish between two cases. First case, x0 minus s is greater than or equal to epsilon. Then s plus epsilon is less than or equal to x0. Since s plus epsilon is standard, s plus epsilon is in B. Recall our definition of B, which implies that every standard real that is less than or equal to x0 is in B. Hence, S is not an upper bound of B. Contradiction. Second case, S minus x0 is greater than or equal to epsilon. Then x0 is less than or equal to s minus epsilon. Hence, for all standard x in B implies x is less than or equal to s minus epsilon. The formula in the red box is internal with standard parameters b, s, and epsilon. Therefore, transfer is applicable, and by transfer, for all x in B implies x is less than or equal to s minus epsilon. Hence, s minus epsilon is an upper bound of B. And hence s is not the least upper bound of B. Again, a contradiction. We have thus proven that s is infinitely close to x0. The following rules apply when calculating with standard parts. For all limited reals x and y, we have the standard part of x plus y is equal to standard part of x plus standard part of y. The standard part of x times y is equal to standard part of x times standard part of y. If y is not infinitesimal, then the standard part of x over y is equal to standard part of x over standard part of y. If x is less than or equal to y, then standard part of x is less than or equal to standard part of y. These rules follow easily from the rules for calculating with limited and infinitesimal numbers. For the first rule, for example, we can conclude as follows. We have x is equal to standard part of x plus some infinitesimal x1, and y is equal to standard part of y plus some infinitesimal y1. Hence, x plus y is equal to standard part of x plus standard part of y plus x1 plus y1, which is infinitely close to standard part of x plus standard part of y. X plus y is limited, and standard part of x plus standard part of y is standard. Since the standard part of x plus y is unique, it must be equal to standard part of x plus standard part of y. Let us look at the natural numbers again. Since R has the Archimedean property, we know that there are unlimited natural numbers, which of course are non-standard. But can we exclude the possibility that there are also limited non-standard numbers in N? That is, that after non-standard numbers come standard numbers again, and only later the unlimited non-standard numbers? This is clarified by the following theorem. Let n be a standard natural number. Then all naturals less than n are also standard. So there are no standard numbers in n that are greater than a non-standard number. The limited naturals are the standard naturals, and the unlimited naturals are the non-standard naturals. To prove this, let m and n be natural numbers, n standard and m less than n. Then m is limited and thus has a standard part r infinitely close to m. Hence r minus 1/2 is less than m and m is less than r plus 1/2. Thus there is some k such that k is an n and r minus 1/2 is less than k and k is less than r plus 1/2. This is clear because we could, for example, take the number m for k. The formula in the red box is internal with standard parameter r. Therefore, the transfer axiom is applicable, and it follows that there is some standard k such that k is in n and r minus 1/2 is less than k and k is less than r plus 1/2. But the open interval from r minus 1/2 to r plus 1/2 contains at most one integer. Hence, this standard k must be equal to m, and hence m is standard. Let's summarize the axioms of calculus that we use in our Red Pill course. These include all axioms of conventional calculus which we adopt unchanged. In the first group, the axioms that deal with the real numbers, and the second group, the axioms that deal with sets and ordered pairs in general. In this lesson, we have added 3 more axioms. In the first group, the axiom of unlimited reals, and in the second group, the axioms of transfer and standardization. This has given us a new view of the universe of calculus. Through our new view of the universe, we have discovered that there are unlimited numbers and non-zero infinitesimals in R. What a surprise! Once again, how did we achieve this? We have introduced a new predicate standard, which is not set-forming, and we have postulated 3 new axioms and left the previous axioms unchanged. Is this allowed? Are the new axioms true? Or are we hallucinating as a result of the red pill, as our fellow students from the blue pill course suspect? Counter question: are the axioms of conventional calculus true? Mathematics cannot answer such questions. But we can give a relative answer. This is a brief digression for those interested in the mathematical foundations in the context of non-standard analysis. Conventional mathematics, including calculus, is normally practiced in ZFC, which is an abbreviation for Zermelo-Fraenkel set theory, including the axiom of choice, where the C in ZFC stands for choice. ZFC includes all the set axioms we introduced in Lesson 1, plus 4 more, called infinity, replacement, regularity, and choice. You can find further details on these axioms on Wikipedia or in any textbook on axiomatic set theory. The primitive notions of the blue pill course, except set and member of, can be defined in ZFC. Since ZFC is a pure set theory and deals exclusively with sets, member of is in fact the only primitive notion. The axioms of the blue pill course can be proven in ZFC. If we add the predicate standard and the axioms of transfer, standardization, and idealization to ZFC, we obtain IST, which is an abbreviation for internal set theory, where idealization is a generalized version of our axiom of unlimited reals. IST is conservative over ZFC, which means Every statement in the language of ZFC that can be proven in IST can already be proven in ZFC. In particular, IST, and therefore our red pill course, is consistent relative to ZFC. A reference for this result is Edward Nelson's article from 1977. So the red pill has no risk, only some pleasant side effects. We can use it in calculus courses without hesitation. Some people are uncomfortable with the axiom of choice and think non-standard analysis absolutely requires it. However, the axiom of choice is not absolutely necessary. If we take ZF, that is ZFC without the axiom of choice, enrich the language by the predicate standard, and add the axioms of transfer, non-triviality, there are non-standard numbers in N, standardization, but restricted to predicates that have at most standard parameters, and standard part, every limited number in R has a standard part, the resulting theory is conservative over ZF, and still sufficient for calculus and more. A reference for this result is the article by Hrbacek and Katz from 2021. What comes next? In the next lessons, we will use infinitesimals and unlimited numbers to define important concepts of calculus, such as continuity, derivative, and integral. We will also prove some theorems related to these concepts. We can always focus on the standard case first and then use transfer to deduce the general case. Are you ready for lesson 3?